ME204, Erratic Rectilinear Particle Motion, Graphical Methods. Well, we already know how to deal with velocity, acceleration, and position that follows a simple, continuous function. For example, when we have a car that drives across our page here that goes at a constant velocity. If it goes at a constant velocity, we can use a simple equation to represent that motion. Our final position is equal to the initial velocity times the time that it takes to drive across the page, plus our initial position, assuming that we have no acceleration. This equation looks very much like a linear equation, where y would be our position and x would be our time. So we have y equals mx plus b to represent the function of this motion. So what do we do when the motion is erratic? Erratic motion is motion that is not consistent. It's not constant. It can be represented by many functions rather than just one function. Let's look at our car again. Now let's assume that our car accelerates for a short period and then goes at a constant velocity and then has a negative acceleration or decelerates until the vehicle comes to a stop. Well, if we wanted to evaluate this kind of motion, we could look at it in terms of the equations that we have already developed. So for the first portion, we would use our constant acceleration equations until we get to the end of the acceleration phase. Then when we get into the constant velocity phase, we could use some more equations to further calculate and represent what the motion is going to look like. And then finally, we would use our constant acceleration equations again in the deceleration phase to complete the representation of this motion. So we have to use a lot of equations and calculate a lot of things throughout the process in order to move through this problem. However, we can use graphs and what we know from calculus to make these problems a little bit simpler to solve in many cases. So let's do a little bit of calculus review. Remember, from calculus, when we take the derivative of a function, it gives us the slope at a point. So for example, if we look at a function like this, if we want to know what the slope is at any point on that function, we would take the derivative of that function and then we could figure out from there what the slope is at any point. The slope is represented by a rise over run. In this case, a short rise of dy over a short run of dx, or a small change in y over some distance dx. An integral of a function gives us the area under a curve. So again, let's look at this same function. Now if we want to know what the area is under that curve from a point A to a point B, like this area, then we can simply take the integral of that function from A to B to calculate what the area is under that curve. This is done by taking a lot of small rectangles that are dx wide by y, the function, tall, and summing them all together to get the total area. So how can we use this information to help us solve problems that involve velocity, acceleration, and position? Well, what if we plot acceleration, velocity, and position each with respect to time? We could then use the slopes and the areas of the graphs to move from one variable to the other. By definition, we know that our acceleration is the change in velocity with respect to time, or dv dt, and that our velocity is equal to the change in position with respect to time, or ds dt. If we look at position, velocity, and acceleration and how we move from one to the other, if we take the derivative of the position with respect to time, we move to the velocity, and the derivative of the velocity would move us to the acceleration. We also know that if we take the integral of the acceleration with respect to time, it gives us the velocity, or the integral of the velocity with respect to time gives us the position. Again, looking at our acceleration, velocity, and position, we can move from one to the other by integrating. If we integrate the acceleration, we get the velocity. If we integrate the velocity with respect to time, we get the position. If we then plot all of these, then we can move from one graph to the other by simply looking at the slopes, or the derivatives, and the areas, or the integrals of the functions. The area moves us from acceleration to velocity and velocity to position. When we integrate, we get the area under a curve. So the area under the acceleration curve would give us the velocity. For example, the area under this portion of the acceleration curve would give us a value for the velocity at this point. The area under this portion of the velocity curve would give us a value for the position at this point. Likewise, if we look at the slopes, it gives us information to move upward through these graphs. The slope of the velocity curve at this point is a constant slope. It's a linear equation, and so it has a constant slope. That constant slope gives us the value of the acceleration, which in this case is a constant acceleration. Also, if we look at the velocity graph, the value of the velocity at this point is 0. Therefore, the slope of the position curve at this point should also be horizontal, or 0. Now, let's consider the car that we introduced at the beginning and look at an example of how we can use this. If we assume that the car accelerates from rest at a rate of 3 meters per second squared, reaches a maximum velocity of 24 meters per second, holds that for 60 seconds, and then decelerates at a constant rate of 2 meters per second squared until it stops. Then we can analyze and figure out how far the car traveled and how long it took. Again, like we've done in the past, we can look at the equations and calculate this for each section, or we can solve this graphically. With any problem, I like to start out by separating out what my variables are and identifying my variables and all of my knowns and unknowns and what I've been given and what I'm trying to find. Here we have an initial velocity of 0 meters per second, an acceleration in the initial phase of 3 meters per second squared. We reach a maximum velocity of 24 meters per second. Our acceleration in the second phase is 0. We are not accelerating. We keep a constant velocity. And then in the final phase, we end with a velocity of 0 meters per second, and we decelerate during that phase, or have a negative acceleration of minus 2 meters per second squared. We want to find our final position, the time that it takes for the car to travel from one side to the other, and also let's look at what our intermediate positions are as well as we go through this process. To solve this graphically, there's a number of steps that we need to take. The first thing that we want to do is align all of our graphs so that the time is at the same distance from the origin for all three graphs. So you'll notice here that we've got the acceleration, the velocity, and position graphs all lined up with time for the x-axis. We're going to assume that the time on each of these graphs is the same at any point along that axis. Next, we want to label the points that we know. So we know that the initial velocity is 0, so we can go ahead and put that point right there on the graph. We also know that our initial acceleration is 3 meters per second squared, so we can go ahead and put that on the graph as well. Now we haven't stated this, but we're going to assume that we're starting from a position of 0 meters. So we'll go ahead and label our position at 0 on the graph, on the position graph. Now we know that our velocity at some point reaches a maximum of 24. We don't know what that time is, but we'll just assume a position and put that there. And we know that it remains constant for 60 seconds, so we can place another 24 meters per second velocity on our velocity graph here. In the final phase, our acceleration is minus 2 as the vehicle slows down. And then finally, our final velocity is 0 when the vehicle finally comes to rest. Now, at each of the known points, we want to draw vertical lines to distinguish the points of change on all three of the graphs. These are the times where we have a change in our motion. This will just help us to separate the different portions of the graph and the different portions of the motion. Next, we're going to connect the known points. Well, in order to do this, we have to relate slopes and areas of the different graphs to create the connections that we need. Now, the first thing that we know is that we are having a constant acceleration of 3 meters per second squared until we reach our maximum velocity of 24 meters per second. So we can go ahead and draw in a horizontal line here, like we've shown, that shows that constant acceleration until we reach the maximum velocity. Now, if we have a constant acceleration, this means that the slope of the velocity graph between these points is also constant, which must be a constant slope at 3 meters per second squared. So we can go ahead and draw that slope in. When we get the maximum velocity, or when we reach that point, it remains constant for 60 seconds. So we have a constant velocity, which means that we can draw a straight horizontal line there connecting those 2 points. Next, we know that our acceleration at the end decreases by 2 meters per second squared, or a negative 2 meters per second squared, until our final velocity is 0. This is a constant acceleration. So we can go ahead and draw that line in as a constant acceleration line, where the acceleration stays at -2 with respect to time until we get to the end of our problem. This also means that the slope of the velocity graph between these 2 points must also be a constant slope of 2, and it's a negative slope. So we have a constant slope of -2 from 24 to 0. That will complete our velocity graph. Now we can complete our acceleration graph. The slope of the velocity graph from 24 to 24, where the maximum velocity occurs, is 0. If the slope here is 0, then our acceleration must also be 0. So we can go ahead and draw in a 0 acceleration across our acceleration graph. Now, if you would like to, we can finish the acceleration graph by connecting the remaining points to make a continuous function. Now that we have the acceleration and velocity graphs, we can complete the position graph. We'll use slopes and areas to determine the points that we need to know to be able to finish that graph. First of all, to move from velocity to position, we integrate, which means taking the area under the curve. If we take the area under this triangle, then we can calculate the corresponding value of position at that same particular time. However, in order to do this, we need to know what the length of the base of the triangle is here, which means that we need this first time. In order to get that time, we're going to look at the acceleration graph. Now the area under the acceleration graph will give us the value for the velocity. So this area of this rectangle must equal 24, or our maximum velocity. In order to calculate that, we need to multiply 3 times the time associated with this part of the rectangle, and that should equal 24. So 3t equals 24. Solving for t, we get a time of 8 seconds. We can go ahead and write that down here at the bottom of our graphs, 8 seconds. Now that we know that 8 seconds, we can calculate what the area of our triangle is here. The area of a triangle is found by multiplying 1/2 times the base times the height. So we've got 1/2 times 8 seconds times 24 meters per second, which will give us 96 meters. So we can go ahead and draw that point in as well. Now, the slope of the position graph gives us a value for the velocity graph, but we can use that the other direction as well. We know that this velocity is 0. If that velocity is 0, then the slope at this point must also be 0. Likewise, if this value for our velocity at the maximum is 24, then the slope of the position graph must also be 24 at that same point. Now we have a linear function here, and we integrate to move down to this graph, which means that if we have a linear function and integrate, we're going to get a second order polynomial, or a polynomial with a squared factor in it. Because our slope is positive, our graph is concave upward. And so we can go ahead and draw in that portion of our graph. Next, the distance from our 8-second point to the end of our constant velocity phase is 60 seconds, making the end of the constant velocity phase ending at a total time of 68 seconds. So we'll go ahead and put that time in there for the total time. The total area under the velocity curve, the total area, will give us the next value for our position. Notice that the value of the velocity remains constant through this portion. So the slope of the position graph between these 2 points will also be constant, and it will be a value of 24 because that's what the value of our velocity is. So if we write an equation to calculate all of this area, we've already calculated this triangle and found it to be a value of 96. We just need to add to it the value of the rectangle. So we have a time of 60, so a length of the rectangle here of 60, and a height of 24. So 96 plus 60 times 24 will give us 1536. So our position at the end of the constant velocity phase will be 1536. And we also know, as we described earlier, that the slope at that point will also be 24. Now we can go ahead and connect a straight line between those, knowing that the slope stays 24 from a position of 96 to a position of 1536. Finally, we need to calculate this last portion of the position. The total area, again, the total area, all 3 pieces of the velocity curve need to be calculated in order to get our final position. However, in order to do that, we need to know the length of the bottom of this triangle, which requires that we know the total amount of time that the car travels from beginning to end. In order to do that, we look again at the acceleration curve and note that the sum of the areas, the total area under the acceleration curve, should give us our final velocity. However, our final velocity is 0, which means that the sum of these 2 areas must also equal 0. Notice that this value is minus 2, so when we calculate this area, it should give us a negative value. So the sum of our first area plus our second area should be 0. So let's write an equation to represent that. Well, we know that this area is 24. We've already calculated that, so we'll go ahead and put that in there. This second area we calculate by taking the height times the base. So my height is minus 2, so I'm going to take minus 2 and multiply that by t minus 68. Now why t minus 68? Well, t will represent my total time from the beginning of the problem to the end of the problem, but I only want this portion. So I'm going to subtract from it this initial 68 seconds. So t minus 68 gives me this portion of my area. Then when I solve for the time, I get a time of 80. That is my total time that the car has traveled from beginning to end. Once I have that, I can calculate this last bit of area and add it to the value that we already have, which is this area. So this area is represented by 1,536, and I'm going to add 1/2 the base times the height of this triangle. So we've got 1/2, 24 times 12. The 12 is simply the difference between 68 and 80. When I calculate that, I get a value of 1,680, which is my final position. Now, again, knowing that our final velocity is 0, we know what the slope is of the position graph. If that's 0, then the slope has to also be 0. Also note that we've got a linear function here, and if we integrate a linear function, then we get a second-order polynomial. Because our slope is negative, it will be concave downward. So we can go ahead and draw in the last portion of the graph. We now have a completed set of acceleration time, velocity time, and position time graphs with all the positions and times shown. We were looking for a final position. We have a final position of 1,680 meters. We have a final time of 80 seconds. We have our position 1, which is 96 meters, and our position 2, which is 1,536 meters. Next time we're going to talk about curved path and projectile motion. For example, what path does a football take as it flies through the air?